let us further discuss vector algebra. So we will discuss addition, subtraction, and scalar multiplication of vectors. Then we'll move on to application of vector at a point and discuss all these concepts with respect to structure engineering, and finally end up with unit vectors. Imagine we have a 2D space which has got bunch of vectors as we see. Imagine we have got this particular red vector, which is defined as v1 having a small dash underneath. And in a column vector, it is 4, 6. So the top place mean that the vector is 4 units in the x direction, or in our parlance, call it E1. And so let us call this E1, and let us call this E2. We will come to E1 and E2 a bit later. Now we assume that this vector V1 has got magnitude of 4 units in E1 direction and magnitude of 6 units in E2 direction. We are interested in adding this to another vector, which we show as a green. Let us take this green vector and put it at origin. We want to add these two vectors. The green vector is having components 4 and 2. So adding these two vector would mean that we will have to add the corresponding components. So 4 plus 4 is 8 and 6 plus 2 is 8. So we get a third vector, a resultant vector, which is having component 8 in the E1 direction and component 8 in the E2 direction. So graphically, what we are saying is that we take one vector and put the other vector on top of it, and then draw a result. The resultant is from the tail of the first vector to the head of the second vector. So the direction of this is from the tail of the first vector to the head of the second vector. This vector, the blue vector, is having component 8 in the E1 direction and component 8 in the E2 direction. And as we can see on this figure, it is component 8, 8 in both E1 and E2. So that's the resultant we get after adding two vectors. Now let us see what happens if we want to subtract these two vectors. Imagine, let us put this resultant outside. Okay, so imagine we want to subtract the green vector from red vector. So we have got the vectors defined as 4, 6 and 4, 2. In order to subtract them, we just subtract the two components, the corresponding components, and 4 minus 4 gives us 0, and 6 minus 2 gives us 4. So in other words, what we are doing is we multiply minus 1 with the second vector and then add it to the first vector. We can call it like that also. So this green vector multiplying minus 1 with this green vector would mean that the magnitude stay the same, but the direction becomes opposite. So this is the same vector. The black one is the same vector as green vector, but its direction has become opposite and its magnitude is the same. So we put the black vector at the head of the red vector. Finally, we get a resultant vector which is 0, 4, and this vector is shown by the purple vector, and its direction is in positive E2, so 0, 4. That's how we subtract the two vectors. Now, what happens if we want to multiply a scalar with a vector? If we want to multiply a scalar with a vector, so again, let's take our red vector, and let us say that I want to multiply a scalar 2 with this vector. So multiplying scalar 2 would mean that the first component will become 8 and the second component will become 12. In other words, what we are doing is we take this vector and we are adding another vector on top of it. And you can see that if we add another vector, sorry, this is not the right place. Let us break it down to 0. So these two vectors are added, and as we can see, the E1 component is 8, 2 times 4 is 8, and the E2 component is 12. So that's how we multiply a scalar with a vector. So this vector, the red vector, has gone twice in the same direction. Multiplying a scalar with a vector, if it is positive, doesn't change the direction. Previously, in the subtraction, we multiplied -1 as a scalar, and that actually made the vector aimed in the opposite direction. So initially it was green one, and after multiplying -1, it became black, which was whose direction was in opposite to the green one. Okay, now as we can see, one question might arise that why are we always bringing all the vectors first of all to origin and then performing the operations like addition, subtractions, and multiplication and so on? Is it got to do with that all the vectors are always at 0, or is there something else? The answer is that in this 2D space where we have got many vectors, we don't know the exact location of these vectors. So this vector, for example, V1, which is having component 4, 6, this can be located anywhere. So it can be anywhere within the space, and we don't know the exact position of this vector. That's why we say that even if this space is a polar space or our cylindrical space, whatever space it is, this vector, the vector magnitude and dimension will stay the same. So imagine if we have a polar space like this one, we can put this over here in this space, and the magnitude and direction of this vector will stay the same. Although we have a polar space, we can have it in a cylindrical space also. In the cylindrical space, we can put this vector anywhere, and the direction and magnitude of this vector will stay the same. And same is the argument with the polar space. So a spherical space, sorry. We can put this vector anywhere, and the vector direction and magnitude stay the same. That's why in our previous lecture, we said that vectors are invariant. They are invariant. We clearly said it. Invariant under change of coordinate. So the fact that the vector can be located anywhere within a space make it invariant in any space. And the type of spaces which we discussed were polar, cylindrical, and spherical. And these are the spaces which are important in our structural engineering. There can be many other spaces, but we are not going into that. So that's where the definition of invariance comes from. But one question arises that if that is true, then in our structure engineering, we need the exact location of vectors. For example, this vector can be a force which is applied onto a simply supported beam. So let us bring this down. Imagine we have got a simply supported beam, and this vector might be a force which is applied over here on a simply supported beam. And imagine we have defined this simply supported beam in a 3D real space. So let us bring this 3D real space, and imagine we have drawn this whole structure in a 3D real space. Now, in the case of structure engineering, if this is a force, we can't just say that the force is applied everywhere. We need, in this space, we need to have an exact location of this applied force. So what we do is we introduce a position vector. Imagine this force is applied at this point. Let us reduce a bit the length of this one. Imagine this force is applied at this location. So how would we find out the position of this. So we would use what is called a position vector. A position vector is always located at the origin to some point. So let us draw this position vector. This is the position vector. Now, I don't know why is this not getting. So this position vector gives us the point where the force vector has been applied. The position vector is not a variable, is a variable vector, or it is a variant vector. Previously, we discussed that the position vector depends on the definition of coordinate system. So this coordinate system, in which we have drawn this simply supported beam, that is a Cartesian coordinate system. This position vector is with respect to, it will have a direction and magnitude with respect to Cartesian coordinate system. But if we change our coordinate system to a spherical or to a polar system, then this position vector will change because our origin might be located somewhere else. So it is important to note that a position vector is a vector which helps us locating a particular vector within a space. And position vector is a function of a coordinate system. However, an ordinary vector, which can be a force vector, velocity vector, acceleration, and so on and so forth, is independent of the coordinate system. Normally in structure mechanics or in advanced structure mechanics, more specifically in continuum mechanics, we use something which is called continuum potato. This is actually a piece which is taken out from a structure. So it looks like a potato. That's why it's called as a continuum potato. And on this piece, we apply all the external loading and try to find out the internal forces developed. So you can see that it has got some external load applied. We are trying to find out some internal forces. Now let us discuss unit vector. As we said, that a vector having a magnitude and direction can be decomposed into components. And if the components are orthogonal to each other, which means to say that if the components are making right angle with each other, then they are called orthogonal components. So imagine we have got this vector v, and it is decomposed into two components, which is 3 and 4, and that is written over here. Now, a unit vector is a vector that go only unity in a particular direction. So the actual component of this v vector goes 3 units in E1 direction or in this direction. But a unit vector will go only unity in this direction, and another unit vector will go unity in the y direction or E2 direction. Hence, E1 vector is 1, 0. So it's going only unity in the x direction or in the E1 direction, and it doesn't have any component along the other orthogonal direction. Similarly, E2 goes unity in the y direction. This can also be written as 3E1 plus 4E2. So our vector V can be written as 3 times E1. So remember, multiplying scalar with a vector plus 4 times E2. Now, just a final word about the spaces which we deal with in structure mechanics. Normally, we deal with 3D spaces, and these are called reals as opposite to imaginary spaces. So we have got real numbers involved in this space. It is shown as a double line R, or sometimes this line is made bolder. And it has got some number as a superscript, and that number gives us the dimension of the space. So if we are dealing with a 3D space, then we would write R power 3. So in this 3D space, we have got all the vectors which are having 3 components, 2 components, or 1 component. So any vector which is having 2 components, like 3, 4, will be a subset of this space. It will be lying in this space. Any vector which has got only 1 component will also be included in this space. However, they can be vectors which can have more than 3 components. It can have 4 components, 5 components. Although our imagination won't capture it. Why? Because we can only imagine 3D spaces, but we can have infinite number of components of vectors. In other words, if our components are bigger than 3, then they won't be we won't be able to capture them. So in the mathematical terms or in algebraic terms, if we have components of a vector, those components can also be called as tuples. So if a vector has got 2 components, we say that this is a tuple vector. If a component, a force, velocity, acceleration, any quantity, having 3 components, we call it 3-tuple. So a tuple is actually an ordered list of number, or in other words, it's an array of numbers. So this is just a fancy word of saying that a vector has got components. So instead of components, we can use as tuple. So for example, if we have got a force defined in a 3D real space, then we can say that this force is of 3-tuple. In other words, it has got 3 components in the orthogonal direction.